Hi everyone. In this video, I will be demonstrating an approach to determining the number of factors when carrying out exploratory factor analysis using RStudio. And the package that we will be utilizing throughout this demonstration is the EFA.dimensions package that was written by Brian O'Connor. So in terms of the data that we're going to be working with and the example, these come in part from an article that was published in PLOS ONE, three-factor structure for epistemic belief inventory, a cross-validation study. And this is an open access article where the authors not only include obviously their article, but also some supporting information in the form of raw data. And so in this particular article, the authors factor analyzed basically a Spanish language version of the epistemic belief inventory, and then they kind of arrived at a three-factor solution. For this particular demonstration here, we're not going to be factor analyzing all the items associated with this measure. We're actually just going to be focusing in on a subset of items that are presented in Table 1. So just to kind of show you, this is essentially the items that we're going to be factor analyzing based on their data. So I will make sure to include a link to the data that we will be using underneath the video description. It's actually saved in an Excel file. So we'll go back to RStudio right here, and the first thing that we have to do is we have to import our data. So you'll need to make sure to go to the session button right here, go to set working directory, go to choose directory, and then locate the directory, the folder on your computer that contains your data. So actually on my computer, there's a folder called EFA Epistemic, and that's actually where the data set has been saved. So I'm going to click on open right here. And so the working directory is set. I'm going to go to import data set. Like I said, this data is in an Excel file. So we'll click on from Excel. And at this point, we'll go to browse and select that data set. It's actually called Epistemic Sub 2, where the S is in caps. We'll click on open, and then we'll click on import right here. And there you go. So now we have our data set. The next thing we want to do is to create a script file. We're going to go to File, New File here, click on RScript, and this is where we will be typing in our commands. So I mentioned that we're only going to be using a subset of the items from this data set here. So you'll see that, we have the first column, we have a subject identifier, we have some other variables at the very end that we're not going to be using, and we're not going to be using all of the 28 items. We're just going to be using 17 of them. So what I thought I would do is to make a lot of the later discussion simpler, is I'm going to create a new data frame that contains just the data from those 17 items. So the current data frame is actually called Epistemic Sub 2. So that's it right here at the very bottom. You can see it. That is just coming up automatically as a result of importing the data. So I'm going to create a new data frame, which I'll call item data. We'll create our little arrow here, and then we'll type in Epistemic Sub 2, and then we'll have a bracket, and then inside the bracket, we'll type a comma, and then everything to the right is going to refer to column number. So I've already identified the columns that we're going to be working with. So I'm going to use the C function, and inside the parenthesis, I'm going to refer to the columns, which basically contain the item level data. So we're going to use columns 2 through 6. So I'm going to type 2:6. And basically the colon is just indicating that we're using the adjacent columns from columns 2 through 6. We'll have a comma, then 9, 10, 12, 15. There's 16, there's 18, 21, 23, and then we'll use columns 25 through 28. So column 25:28. So then we have our end parenthesis here to close out that C function, and then we have the final bracket to close out our references to the columns within our original data frame, which was Epistemic Sub 2. So we'll highlight all of this and click on Run. And then if we just want to take a quick look at the structure of the data, we'll use the structure function, str, and we'll type in item data. And then from there, we'll highlight it and run. And so now you can see we have the data frame that contains our item level data. Okay, before we, now actually at this point, let's go ahead and use the library function, and we'll go ahead and open up the EFA.dimensions package. So I'll type in library, and then we'll type in EFA.dimensions. Okay, make sure that you have EFA all in caps. So we'll highlight this and run it. And so now you can see down below it's ready to go. So before I actually go through and show various functions to determine or make judgments about the number of factors, just keep in mind that the determination of the number of factors is a very important part of the exploratory factor analysis process. And what you don't want to have is a situation where you overfactor or underfactor. Now, a lot of times, folks, when they are carrying out factor analysis, they'll use maybe one or two rules. Oftentimes, these rules are not grounded in any kind of firm strategy, but rather these are just kind of what are given to folks. Probably the most common rule that folks use is the eigenvalue cutoff rule. Or basically the Kaiser criterion, which essentially states that you retain the number of factors with eigenvalues that are greater than 1. Now, this particular strategy is historically regarded as very problematic. It oftentimes leads to overfactoring. It's not one of the more encouraged approaches. There's also the use of the Scree plot, which is kind of a visualization of eigenvalues from your correlation matrix that's plotted against factor number, and then you're just basically kind of identifying visually where there might be a break between more major factors and then perhaps kind of trivial factors, if you will. So those are two very common approaches, but really when it comes to making decisions, there are a lot of other approaches that are much better. And so in this particular video, I'm just going to kind of show you a few strategies or a few approaches that you can use either in concert with or in conjunction or instead of, say, the eigenvalue cutoff rule. And just kind of keep in mind that these different approaches don't necessarily all agree. And so what I've kind of done is thought about this in terms of, evidence or creating kind of an evidentiary base. And so I've kind of created a table where I have these different approaches listed, and these are the approaches that we'll be going through in this video. And then, thinking in terms of, what are the limitations of the various approaches and what do they end up concluding. So I'm going to show you really quickly a slide that I created with some of these different approaches indicated. So as you can see right here, I've got on the far left, I've just got basically different indicators. So you can see I've got parallel analysis. That first row is just kind of a general reference to parallel analysis. Then I've got parallel analysis involving an unreduced correlation matrix, parallel analysis using a reduced correlation matrix, the map procedure, Scree test, sequential chi-squared tests, a lower bound 95% of the RMSEA, empirical Kaiser criterion, and then kind of the interpretability of various factor solutions. So you'll notice that under the notes column, I have just various comments regarding these different procedures and potentially maybe where their limitations might be, at least based on some of my review of the literature. And then on the right, I've got a column containing various functions or commands that we'll be using in this video presentation. So based on each of these, they should suggest a number of factors, and then we'll kind of make our determination from that. So let's go ahead and move back into RStudio. And the first thing that we're going to do is we're going to carry out a parallel analysis. So what I'll do is the function for this is going to be RAWPAR for basically parallel analysis on the raw data. And inside the parenthesis, I'm going to type in item data, which is the our data frame containing the subset of items. So then we'll type a comma, and then we're going to refer to the factor model. So there's a couple of approaches that we could use. One is to essentially carry out a parallel analysis using an unreduced correlation matrix. Basically, this equates to a PCA approach, which I'll do right now. I'll just go ahead and type in factor model here, set this equal to, and inside parentheses, PCA. The other approach is to perform the parallel analysis assuming a common factor model, which we might then use something like principal axis factoring. But for this first one, we're just going to rely on the PCA approach. We're going to refer next to the number of data sets, basically the number of replicates, which we'll type in capital N data sets, set this equal to, and for this demonstration, I'll use 1,000. Then comma, and we'll also have an argument for percentile. We'll set this equal to 95. Okay, so at this point, if I highlight this and run it, it takes a second, but you'll see that we get just kind of a general description. And then you can see down below, we've got comparing the real data eigenvalues against random random eigenvalues, basically the mean and 95th percentile of randomly generated eigenvalues. So in this data set right here, the basic idea is that we retain the number of factors with eigenvalues that were generated from the data that exceed randomly either the mean or the 95th percentile of randomly generated eigenvalues. So that's why we have this mean column and a percentile column. The percentile column contains the 95th percentiles of the randomly generated eigenvalues. And so you can use either one of those. Probably the percentile approach is a little bit more conservative approach in terms of retaining factors. For this demonstration, we'll go ahead and stick with the 95th percentile approach. So right here, we've got the first eigenvalue from our data is 2.931. The 95th percentile, we have 1.322. So our observed eigenvalue exceeds the randomly generated eigenvalue. You can see that the second of our observed eigenvalues exceeds the randomly generated one. Then in terms of the third factor, the eigenvalue is greater than the randomly generated eigenvalue. And then with the fourth factor, you can see that the eigenvalue from our data is less than the 95th percentile of the randomly generated eigenvalue. So what that would mean then is that we would retain three factors based on this particular approach. And if you scroll down, you'll see there it is, just a little bit of a note that says we would be using or deciding on three factors to account for the intercorrelations among our variables. So the other approach to this, what I'll do is I will actually go ahead and copy this and paste it. And we're just going to make one little change right here. Instead of PCA, we'll use PAF. So if I highlight this and click on run, so this is using principal axis factoring, and it's the same approach in terms of the comparison between observed eigenvalues and those that are randomly generated. And you'll see that essentially where things kind of break off is after the fifth factor. And so in fact, the number of factors according to parallel analysis using this method is 5. So right now we've got really one approach, or one of our parallel analyses is suggesting 3 factors. The other one is suggesting 5 factors. So, basically, if we go back to this slide right here, that basically means then that the first 2 rows after that top row would be a 3 and a 5, which now you can see. So then the next step that we're going to take, we're going to use the map test using the EFA.dimensions package. So let's go back into RStudio. And in this particular case, all we need to do is to type in map, all in caps, and then inside the parenthesis here, we'll type in item data. Okay, so at this point, all we do is we just highlight this and click on run. And essentially what we get is we get our output. These are Velleser's average squared correlations. And then basically at the very bottom, you can see that we've got the number of components that's suggested based on the map test. And really, there's a couple of approaches right here. Both of them are actually suggesting basically a one-factor model to account for the interrelations among the indicators. But really briefly, the way this was arrived at is if you look at right here in this section, you'll see that we've got root, you'll see we've got 0. Basically, what's happening is that at each step along the way, components or principal components are being extracted, and then the remaining average of the squared partial correlations are being computed. And so that's basically what's going on. So this first step right here, where there's no principal component that's extracted, this is literally the average of the squared zero order correlations among the variables. Then we extract the first principal component and compute the remaining, the average of the squared partial correlations after kind of controlling for or removing that first principal component, and then so forth. And so in a nutshell, what we're doing as we go through is we're just extracting more and more components and then computing the average of the squared partial correlations. And so essentially what we're looking for is the average of the squared correlations in this column that are that is the smallest. And so it turns out that the smallest of these values happens to be this number right here, which is associated with essentially removal of the first principal component. And so that's where down here it says the smallest average squared correlation is that number that we just saw. And then this is why we have the number of components using the map test as 1. And so that's the number of factors that would be recommended based on this test. So if we go back into our table here, you can see that in this particular case, we've got the map suggests a 1-factor solution. So we have 3-factor solution suggested by the PA on the unreduced correlation matrix. We have a 5-factor solution suggested when we carry out our parallel analysis on the reduced correlation matrix, and now MAP is suggesting a 1-factor model may be possible. Okay, so the next thing that we will use, or the next approach we'll look at, is the Scree test. So I'll type in Scree _plot, and inside parenthesis we'll refer to our data frame item data right here. So when I highlight this and run it, you can see the plot on the right emerge. So you can see this right here. So basically along the y-axis, we have the eigenvalues, essentially from our unreduced correlation matrix, plotted against the components. And as you're looking at this, you can see that there appears to be 3 most likely dominant factors, and then as you can see down below, the rubble at the base of this plot. So basically this would kind of visually suggest perhaps a 3-factor solution. And if it kind of helps, what we'll do is just quickly highlight sort of the break point, if you will. So let me see if I can find this here. Yeah, so you can see there's appears to be 1 dominant factor here, another dominant factor, another dominant factor. And then it looks like, we have this sort of break, almost kind of an elbow. And so we end up retaining those factors that fall above that elbow. So that's basically the idea. The one limitation of the Scree plot right here, it looks fairly obvious, but the Scree plot can become a little bit more difficult to interpret under certain circumstances. Sometimes there's more than one apparent break, and so it may be a little bit more tricky to identify the number of factors in those contexts. But anyway, looking at our Scree plot, we have some visual indication of perhaps 3 dominant factors that may help to explain the interrelations among our measured variables. So given that, I've gone ahead and just added a 3 right here to signal that that would be the suggested number of factors. So next what we'll do is we'll move on to a series of sequential chi-square tests in order to further help us in making our determination. So the next step, we'll go back into our script window, and I'm going to type in the command SMT, and inside the parenthesis, we'll type item data yet again. So in fact, we're going to get both chi-square tests as well as an indicator with respect to the root mean square error of approximation. So I'm going to go ahead and highlight, click on run right here. And so we have a sequential chi-square model test. So basically these are testing the fit of different factor models. And if we're, in terms of using this test, the general approach would be to go through a series of testing a 1-factor model, a 2-factor model, 3-factor model, and so forth, until a point at which the p-value that's associated with the chi-square test becomes non-significant. And a non-significant p-value is actually regarded as an indicator of fit. So if you think about it, like for instance, if we look at the 1-factor model right here, we have a p-value that is indicating statistical significance. That's actually, the null is actually good fit or exact fit. And so if this is significant, that's reflecting a significant departure from exact fit. So you can see that down here where it says 6-factor model, we sort of transition from a significant 5-factor model to a non-significant 6-factor model. And so with that, it would suggest a 6-factor model may be the best representation of the relationships among our variables. And that's what we get right here in terms of this particular statement. Okay, so based on our set of chi-square tests, then it would suggest a 6-factor solution. So I'm going back right here and just kind of noting that. Just kind of keep in mind that these chi-square tests, because factor analysis is a large sample technique, and these chi-square tests are going to be more powerful in larger samples, a lot of times this can lead to over-factoring. So I'm not sure that I would put much weight on the 6 factors that's proposed right here. The other thing I do want to mention, I actually have kind of modified this sheet just a bit, that lower bound of the 90% confidence interval for the RMSEA that I had mentioned before. Actually, that is associated with the EFA tools package and not Brian O'Connor's EFA.dimensions package. So I just kind of removed that. So it looks a little bit different than what we had before, but that's just to be, again, we're focusing in on using the EFA.dimensions package in this particular video. Okay, so now we'll go ahead and look at the empirical Kaiser criterion. So we're going to type in EMPKC, and inside our parenthesis, we'll type in item data, again, referring back to our data frame. We'll type in core kind, set this equal to, inside quotation marks, we'll type Pearson right here. So then for this one, we'll highlight it and just take a quick look. I will click on it. And so basically we're kind of using a similar a logic that we use with parallel analysis. In this case, we have the eigenvalues from our data as well as reference values right here. And so basically we maintain those factors that have eigenvalues that exceed the reference values. And once we have a reference value that exceeds the eigenvalue from our data, then at that point we make the cut, so to speak. So you can see that the first eigenvalue from our data exceeds this reference value. The second one exceeds the reference value. The third one exceeds the reference value. And you can see that for the 4th factor, that eigenvalue from our data is less than the reference value. So that means that we would maintain a 3-factor solution based on this criterion. If we scroll down, you can see it says that the number of factors according to this criterion is 3. So basically, going back to our table here, we now have, I've just noted 3 factors. So you can see that, really with 3 of our approaches right here, we have a suggestion of 3 factors. We also have a 1-factor solution suggested, as well as a 5-factor solution. And so, we basically have then maybe 2 candidate numbers of factors, a 3-factor and a 5-factor. So at this point, there's no real clear consensus, but we do have some greater indication that that potentially a 3-factor model may work best. So what we can do at this point, we sort of reduce things down just a bit, and we might compare a 3-factor model and a 5-factor model in terms of their interpretability. So essentially just performing the exploratory factor analysis and performing some type of rotation and then interpreting those factors. So at this point, I'm going to use some commands, again, associated with the EFA.dimensions package. We'll type in basically PA_FA. Basically, what we're doing is parenthesis axis factor analysis. So I'm going to type inside the parenthesis here, I'll refer back to my data frame name, item data. We'll type in core kind, set this equal to Pearson. So that's the type of correlation matrix that we're going to be working with, Pearsonian correlations. We'll type comma, and then we're going to type in N, capital N, then factors, and we're going to set this equal to a number. So we have 2 candidates here, a 3-factor model and a 5-factor model. So I'll start off with a 3. So I'll type in N factors, and it should say factors with an S on the end. We'll set this equal to 3, then comma. I'm going to go ahead and use this option right here, basically ITER-PAF. This is basically the number of iterations. We'll set this equal to 50, comma, and then we'll type in rotate. So you have to decide on what kind of rotation method you want to use. So, you have options for both orthogonal and oblique rotations. For this demonstration, I'll go ahead and use Varimax rotation. I've already actually run the analyses and the correlations among the factors. I used Promax rotation. The correlations among the factors were rather low. So I'm going to simplify things a bit by sticking with a Varimax rotation. So I'm going to type rotate equals, and inside the quotation marks, I'll type in Varimax. Okay, so at this point, we'll go ahead and highlight this and click on the run button right here. And you can see that we get our factor analytic results. So you can see it's quite a bit of information. They give you right here, they give you the initial communalities and the extraction communalities. The initial communalities are basically the squared multiple correlations between each of the variables and the remaining variables. Okay, so think about it as regressing each indicator onto the remaining indicators. The R-square value would be the initial communalities. And then the final extraction communalities is an estimate of the proportion of variation accounted for in each item that's accounted for by the set of factors that you have extracted. So we'll go ahead and scroll down. You can see that we've got just a breakdown of the initial eigenvalues from the unreduced correlation matrix, as well as proportion of variance accounted for, and so forth. Actually, let me rerun this and kind of clean it up just a bit here so it doesn't look so strange. So there you go right there. We'll scroll down. You can see it gives you the number of iterations. It converged on 8. You have some model fit statistics right here, which are really handy for evaluating the overall fit of the model. For instance, a common fit index that's reported would be RMSEA right here. Basically, RMSEA values that are less than that are 0.05 or less would be regarded as an indication of close fit of the model to the data. And values that would be up to about 0.08 would be considered acceptable, and then values greater than 0.10 would be considered indicating poor fit. You also have the CFI right here, if I can highlight it. And basically this value, the theoretical range is between 0 and 1. Values closer to 1 indicate better fit. Values greater than 0.9 would be considered acceptable. Generally, values at 0.95 or above would be considered more optimal levels of fit. So we'll scroll down. You can see that we have the unrotated factor loadings. If you scroll down a little bit further, you can see that we have a breakdown of the 3 factors that are extracted. So you got factor 1, factor 2, factor 3. These are the eigenvalues associated with each of those factors, as well as the proportion of variance accounted for by each of those factors. When you scroll down a little bit further, you've got the Varimax rotated loadings. So these are the factor loadings after extraction and rotation. And so basically what we're doing in this case is we're looking at each of the items in relation to each of the factors to identify which items best capture aspects of that factor. And so there are various loading criteria that people use. A very common one is if you have a loading of 0.30, at least 0.30, let's put it that way, then that would be an indicator that that particular item is a reasonable measure of that particular factor. When I say 0.302, I mean it in absolute value. Some people use a little bit more conservative approach. That tends to be my preference. I generally prefer a minimum loading of 0.40 to designate an item as an indicator of a given factor. But for this demonstration right here, we'll just go ahead and stick with the 0.3. And so you can see right here that looking at item 3 right here, you can see it loads at there's a negative 0.45 right here. That would meet the loading criteria of 0.3 and even the 0.4 that I prefer. And you can see that it loads much lower on these other factors. And so this particular item would be regarded as an indicator of factor 1. Then you've got item 5 that also exhibits a strong loading, as well as this item 8 from our measure. And then also we have item 9 that would also meet the minimum loading threshold. Then you can see we've got item 14, item 15 right here, item 20 right here, item 24, excuse me, and then item 27 right there. So we've got a number of items on factor 1 that would meet that minimum loading criteria and that really actually load much lower on the other 2 factors. So we would use those items to kind of name that factor, and hopefully if it makes theoretical sense, then we can kind of give that factor a meaningful name. In terms of factor 2, we've got item 4 right here, correlated highly with that particular factor. You can also see we've got item 25 and item 26 also highly related to that factor. And then we've got on factor 3, you've got item 2 right here, item 11 right here that would meet the minimum loading criteria, item 17, item 22 right there. And so we would use those items to name factor 3. So what I did was I just kind of created a table using those items from table 2 from that article. So these are the items, the content of those items. And then I essentially am using those loadings that kind of meet the minimum threshold. Again, we were using 0.3 to name those factors. And so you can see that in that first column, factor 1 really largely contains items that are measuring beliefs in fixed ability and quick learning. So this is from an epistemic belief inventory, basically beliefs about the nature of knowledge and the nature of basically the nature of knowledge. And so these are beliefs related to fixed ability and quick learning. So these items are all consistent with that. Factor 2, we only had 3 items that really met the minimum loading criteria on that. These items were basically reflecting a belief that knowledge comes from kind of omniscient authorities. And then factor 3 was really kind of a blend of items measuring belief in simple and certain knowledge. And I will say that I was a little bit confused going back and looking through the article and everything. The loadings are actually kind of strange given that there's a couple of items, item 2, and I believe, let's see. Yeah, item 2 and item 22 are actually worded in the opposite direction. I think those would be reverse coded items in the original scale. There was no mention of any reverse coding, but for these items to be loading in a consistent fashion with the in the same direction with the simple items, it would seem that they would have had to have reverse coded these. So anyway, I'm going to make that assumption, and we'll call factor 3 belief in simple and certain knowledge. So then what we'll do is we'll check out a 5-factor model. So I'm just going to copy this and paste it down below and just change the number of factors to 5. And so we'll highlight this and run it. And so now you can see that we get our 5-factor model represented in our output. You can scroll down, you can see that we have each of our 5 factors noted along with the eigenvalues and proportion of variance. These are the unrotated eigenvalues and proportion of variance accounted for. When you scroll down below, you'll see that you've got the Varimax rotated loadings as well as a breakdown of the eigenvalues and proportion of variance following rotation. So just kind of keep that in mind. If you scroll back up here where it says unrotated loadings, the next part of the output contains the variance accounted for with the unrotated factors. And so if you scroll down a little bit further, you've got the Varimax rotated loadings, and then you've got the variance breakdown associated with those rotated factors. So make sure that you keep those together in your mind, so to speak. So at any rate, in terms of the rotated loadings, we have 5 factors that have been extracted, and then we have with these Varimax loadings, these are basically just the correlations between each indicator variable and those particular factors. And I've gone ahead, rather than go through this thing, I've gone ahead and just put together another slide where I've kind of give a breakdown. Okay, so here is my slide, and you can see that what I did was I just included those items that met the minimum threshold of 0.30 in absolute value. And just kind of looking at this, I had basically in column 1, the items that sort of fell onto factor 1 appeared to kind of reflect sort of a blend of the innate ability and speed of learning factors or quick learning factors. They really kind of seem to suggest sort of a belief that smarter students are going to be faster learners. So then we have factor 2, where we have the belief in omniscient authority. Basically, knowledge comes from omniscient authorities. Factor 3 contains that familiar configuration of simple belief in simple knowledge and certain knowledge. Factor 4 looked to be more of a pure measure of belief in quick learning. And then factor 5 really kind of looked at sort of innate ability items that are focusing on sort of more of a general intellectual ability perceptions. Now, the thing to kind of note here is that looking at this, we only have 2 items that met the inclusion criterion on this particular factor. And one of the things to keep in mind is that, whatever factors you extract, you need to have at least 3 indicators basically that contain non-trivial loadings in order to define that factor. And so in this particular case, we've got 2 loadings that are actually fairly substantial, but there's only 2 indicators of this particular factor. And so there would be some question about whether or not this would be replicated in another study in terms of that particular factor. So given that, and maybe some incongruence with with theory, then probably that 3-factor model would be a better representation of the associations among these measured variables. So as a result, I've gone ahead and decided to just indicate a 3-factor model best reflects the associations among these indicator variables. Okay, so that's going to kind of wrap up this presentation. It was a lot to cover. If you go underneath the video description, again, you'll find a copy of the Excel data file. I'll include a file that contains the syntax that I've used, but you can see right here the functions that I was using as I went through this presentation. I'll also include these two slides that I was using in this video presentation, so you can kind of refer back to that. Again, my strong encouragement is that you try to avoid just using the conventional or the historic standard of the Kaiser criterion, basically the eigenvalue cutoff rule, and consider some of these other approaches to making a determination of the number of factors. Basically, you end up with a much more robust picture of the number of factors, and that's what I believe we've accomplished here. So that's going to wrap up this video presentation, and I appreciate you watching.